let's discuss maybe with first going towards timing synchronization, which is essential for identifying photons from the same entangled pair at the remote end nodes. So these photons are generated or created at the same time. They travel through different lengths as they reach their end nodes, but it is expected that you should be observing coincidences at these two end nodes if there is strong timing correlations in these photons. However, there are drifts in the link, like we talked about, and having the same timing reference at these two non-local end nodes is essential in order to tag these detection events and use them to derive the coincidences as the true coincidences that should have been detected at these two end nodes. As we've seen, the fiber link introduces timing drifts, and for time tagging, there is careful alignment that is required, and any offset that is introduced has to be corrected for. There are several approaches that have been explored, and it would be great to sample some examples that gives us some understanding on these techniques that are used for compensation. We should remember that this is much evolving field, and new techniques continually emerge. Here we show one example that you see in the bottom left corner, where a rubidium clock at the source node is used to distribute 10 megahertz clock reference using a classical optical signal to both the remote nodes. This uses something called the White Rabbit timing references, where White Rabbit is a protocol that was developed at CERN to provide sub-nanosecond synchronization, and it combines the precision time protocol with physical layer clock recovery and phase tracking, allowing highly accurate distribution of clock reference. And this is, for example, tested here across a link distance of 50 kilometer going from the source node to the two end nodes. The classical reference that was used shares the same fiber with the quantum signal. And this is done with wavelength division multiplexing. That is, the two signals, classical and quantum, they occupy different wavelength bands. And at the end nodes, the classical reference is used to tag the arrivals of the photons. So this enables precise coincidence measurements over distances that are separated as large as 50 kilometers shown here. And in such examples, eliminating the crosstalk that can occur from the classical reference to the quantum signal is of importance. And this requires some characterization and studies to determine whether the operation can be successful. And what we can note here from this example as well is that the drifts that the classical reference and the quantum signal see going through the same fiber is going to make sure that there is in fact synchronization at the two end nodes. For example, if this was done over different fibers and those two fibers would see different drifts over time, this wouldn't be as successful. In another approach that you see in the center figure here, detection at one node was used to generate classical optical pulses that travel along the same fiber as the quantum signal, but this is done in a time multiplex manner. At the receiving node, the pulse that was sent from the first node is used to gate the detector, that is, open the detector to accept photon detections for a precise time window. And as these two quantum and classical signals travel the same fiber link, this automatically accounts for the drift in the link, and the detectors will be timely opened for accepting the photon, and hence the coincidence detections become possible with the time tags accurately determined. And let's consider another example where, in the third case, GPS clocks were used as global time reference. However, for long links, fiber introduced drifts also need to be taken accounted for. So that's something we have observed from the last two examples. So in this demonstration, which was conducted over hundreds of kilometer distance, so you can see close to 250-kilometer distance between the end nodes, and then there is a source node in the center. In this demonstration, it is done. The drifts is compensated for by monitoring coincidences of entangled photons to determine timing offsets, and that allows for correcting the reference accordingly. although the reference is first based on GPS clocks. So these examples are of approaches, each of which that can have trade-offs depending on the link and application. And these are some considerations that we can dive a little bit more detail into when we think about synchronizing two non-local remote nodes. The precision that is required really depends on which degree of freedom is used for encoding and what is the application. If you're using, for example, frequency encoding, the timing requirements can be extremely tight. In such cases, there's a requirement for tens of gigahertz scale radio frequency signals that should be distributed, and the jitter needs to be much smaller than the RF period, and it can even be down to sub-picosecond requirements depending on the qubit bandwidth. In the case of polarization encoding, the requirements are typically less extreme but still tied to source bandwidth and detector jitter, and often the jitter in the detectors will be around 100 picoseconds down to 3 picoseconds, depending on the demonstration of the detectors that have been used so far. The application also plays a vital role here. For example, in a belt test, active basis switching must occur faster than the time of flight of the photon between the nodes so that the locality loophole is closed. And there are other practical factors that one can include to decide which approach must be utilized for timing synchronization. And this could depend on pair generation rate, that is, how fast photons are being generated and sent down the link, and link distance and loss as well, which determines amongst all these photons that are generated and sent down the link, how many of them actually reach the link. And this affects the synchronization options that are present that could be utilized. And finally, timing jitter from the link itself as well, the drifts due to temperature fluctuations and environmental factors, all of these put together. So, with that in mind, if there is enough correlated photon pairs that actually reach the end nodes, so that the quantum signal itself can be used for synchronization, that's a great choice, and that can be helpful because it can reduce the amount of additional hardware that might be needed. Uh, on the other hand, a classical reference could be used either in a separate fiber or the same fiber, depending on the level of drift that is expected and whether it's repeatable in another fiber. But mostly, another reference that shares the same fiber with the quantum signal, like we saw in those examples, can be used. And such coexisting classical quantum signal choice it helps with fast link drifts, and it really depends on the link having very fast drifts versus the link being short, and it could potentially have smaller drifts and could benefit from using quantum signal itself rather than the classical signal. So we have noted here that with classical references, it allows for higher power and faster corrections, whereas the quantum-based synchronization can be limited by photon flux. But this is really dependent on the link distance and the losses like we talked about.